For solving a particular problem, we have to pick up a suitable algorithm that gives us the best performance. Now for a particular problem, there may exist multiple algorithms. Now which algorithm has to be picked up? Now we can decide based on the time complexity of the algorithm, which are normally expressed in some asymptotic notation, conventionally the big O notation, the loose upper bound. But only this upper bound should not be one criteria for selecting the algorithm for a particular problem to be solved. Many times the number of data that has to be handled, if they are smaller, then an algorithm that is not better in time complexity from the asymptotic notation point of view still give us a reasonable result. At the same time, the user has to know about the basic operations that are involved in the different algorithms, because many a time not a single algorithm but the group of algorithms and their internal operations in a suitable manner may give us the best performance. For example, let us take a sorting algorithm. There are many sorting algorithms available. Out of them, bubble sort, insertion sort, selection sort. They are taking n square time in their worst case, but they are very easy to understand. Their internal steps are very simple. On the other hand, some sorting algorithms like quick sort, merge sort, heap sort, they gives us better performance, but their internal operations are very difficult to realize. Now, if a particular problem has been given to us, then say sorting a bunch of answer script, where each answer script are on the top of it, the roll numbers are written. Roll numbers may be again 6 to 8 symbols. Now to sort those bunches of copies, which sorting algorithm will use? Now if some constraint has been laid down that one person can hold only maximum 20 copies on his hand, then which algorithm or which combination of the algorithm or which steps of different algorithms may give us the best performance in a particular scenario? Now after that the problem has been defined, the first question that should come to our mind is that what is the collection size? If the collection size is less than or equal to 20, then we don't have to go for some better algorithms like quick sort, merge sort or heap sort. Simple algorithms like bubble sort, selection sort or insertion sort may give us the better result in that scenario. Because for this low value of n, finally the n square value may be comparable with n log n. Okay, now let us go for bubble sort. What will happen if we follow the bubble sort algorithm in that scenario? Now the internal operation involved in a bubble sort is the exchange. Now in the exchange operation, if we try to write the statements for a particular computer program that involves 3 different states, but if we have to implement that on our given problem, that actually involves only 2 operations, that simply removal one copy and putting it in a new position. But this bubble sort algorithm, if we apply on that problem, it may lead to some unnecessary operation. For example, if the largest roll number is in the first position, then we will insert it in the second position. Again, it may happen the third position is smaller than this one, so we will again insert in the third position. That procedure will be repeated for all this 20 times there. I am assuming that we have 20 copies with me. But out of these 20 insertions or 20 removals, only one removal and one insertion is the required one. Remaining 19 are unnecessary. But bubble sort algorithm, if we follow the algorithmic steps, we cannot avoid that. So, bubble sort algorithm may not be the suitable option for that purpose. Now, if we go for a selection sort algorithm, now that drawback is overcome. Because in a selection sort, we don't have to go on inserting this element again and again. We will simply remove that copy only once and put it in the last position, or wherever that copy should go. But difficulty that we will face in the selection sort algorithm is that how to remember about the copy, which one is the largest roll number. Okay, anyway, as a human being, we can find out our own techniques so that we can displace that copy a little bit, which one is the currently large, and whenever we get a next larger one, we'll make it is a mark it as a current larger, and earlier on we again merge the normal situation there. In that way, we can minimize the unnecessary operations, but still the problem of remembering that will be still there. But in this situation, the insertion sort algorithm may give us the best performance, because we can start with only one copy at our hand and simply take the next copy from the remaining ones and go inserting it on the sorted part here. So this procedure may be applied. So by using the insertion sort algorithm, we can sort these 20 copies at our hand. Now let us take a different scenario. Now let us increase the number of copies to 100. Now if I again try to perform the insertion sort algorithm on these copies, now it will be difficult for the person, because now he cannot hold all 100 copies on his hand. Now we have to think whether can we apply a different algorithm or can we merge two algorithms to solve the problem. In that case, we can get the solution in the merge sort algorithm. In a merge sort algorithm, we need two sorted lists. Then we can go for merging this sorted list. And worst case time taken by the merge sort algorithm will be of order m plus n, where m and n are the size of the two lists. Now in our example, if we divide the whole 100 copies in bunches of 20s, we will get 5 bunches. Now every bunch of 20 copies we will sort by following the insertion sort algorithm. Then these 5 bunches of sorted copies, now we can merge them to get a sorted list of 40 size. Then again two bunches of 20 copies will again merge it. We will get again to 40 copies. Then we can merge this 40 copies to get the 80. In that way we can repeat it. That means the merge operation of the merge sort algorithm along with the insertion sort can give us a better solution in this second scenario. Now, but if we try to perform the merge operation merge sort algorithm directly on this 100 copies, then in the last level we have to merge two separate parts of 50 sizes, and in the worst case we may have to go for the 100 operation, because the worst case situation for merging will be that every alternate element are present in one list. Other contains the in-between elements there. So every time we have to pick up from two different lists. That will was the maximum amount of time. But on the other hand, we can see that the best case for merge operation will take only half of that means only n operation. So that n is the minimum of m and n. So best case of the merge operation will be that if the two lists are totally disjoint. But again, in our problem, that step will take a constant amount of time, because now the merging operation of these two bunches of copies will be simply the keeping one bunch over another one. That means a constant time. So after getting this sorted elements there, we can merge them there. But since our list size was very small, only of 20 size, now we can go for a traditional merging operation there. Now let us go for a third scenario. Now if our data size is near about 1000. Now if we go on dividing the list of only 20 size, then we will get 500, near about 50 branches there. Now go on merging those lists there. At the last level, we will get the copies of one batch having 500 copies, and in the worst case of merging these two lists, we will go for 1000 operation. Now, if we try to take the advantage of the best case scenario of merging, then this merge operation time can be minimized. But the question is how? How will ensure that these two lists that are merged are disjoint? Now if we just closely look at some other sorting algorithms like bucket sort, we may find a solution there. In the bucket sort algorithm, after putting the data in the different buckets, we will get the restored list by simply appending one bucket after another one. Here we have got the strength that each bucket are disjoint. Now, if we apply this concept in our current problem, instead of dividing the whole answer scripts in a random group of 20s, now by scanning all the copies only once, if we can form some buckets based on the first character, first symbol, that may be a digit, maybe a character, then we can form some buckets there. But again, this option also may not give us the best result, because sometimes a bucket again may become a very larger one that may not be handled by any of the first two scenarios. Now if we get a larger size bucket, maybe larger, more than 100 copies, then we can make a subgroup of that particular bucket again based on the second symbol in the roll number. And this procedure will be repeated till all these groups that we are getting are of handleable size. After all these groups has been created and all are of handleable size, either of 20 or maximum 100, we can adopt the method that are applied in the first scenario as in the second scenario. So in that way we can get the sorted list, sorted bunches of copies there. That may be maximum of 50, maybe of less than 50. But we have ensured that all such bunches are totally disjoint. Now after we have got this all the sorted bunches, now simply we have to go on putting one bunch over another one. The largest roll number at the bottom, then over that simply to put the just smaller bunch over that. If in that way we can proceed, then all these 1000 copies can be sorted in a very short amount of time. Now just in this third scenario, you can see that the techniques, the internal basic operation of 3 different sorting algorithms. Insertion sort, where we applied the insert operation. Okay, insert in a sorted list. Then the merge operation of merge sort algorithm. But we have ensured that all this, the merge operation will encounter only the base case scenario. And for that one, we have adopted the bucketing operation of bucket sort algorithm. Now, once these internal operations are realized, a person can understand the strength of the algorithm, because all algorithm success is lying on their own internal fundamental operation. Now if we go for the quicksort algorithm, the partition operation is the main operation that gives the success to the quicksort algorithm. But partition operation itself is very difficult to understand. If someone don't realize why the partition is created, how these partitions are reducing the problem size, then person will not understand the algorithm. But it is very difficult to realize it. Similarly, the theoretical best algorithm of sorting, that is the heap sort algorithm, that is always taking worst case n log n time, and you don't need the additional memory also like the merge sort algorithm. But still, it is very difficult to realize this algorithm because the internal operation on the heap sort is a heapify. And during the heapify operation, which data is moving to which other position is very difficult to realize. So, if someone don't realize the internal operation, he will not definitely understand the algorithm. And this is the best technique to realize about the internal operation, to map it with some real life situation there. Now, in our daily life, we are performing many such operations where without our knowledge itself, we are using some data structures operation. So, I think this is the way that we have to present our algorithms, that we can easily map it to some real life problem, that we are always handling that one and simply map it to the algorithm. These sorting algorithms performances is asymptotically the insertion sort algorithm may not give as a good result, but for a smaller collection it gives as a better solution. And we, in this presented problem, we have taken that one as a basis one, and success of the later situation also is depending on the performance of the insertion sort itself. Though theoretically insertion sort may not be the best algorithm, but this sequence of operations, bucketing, insertion sort, then merging, they may give us the best solution. Thank you.